Hey everyone, so let's talk about two of the biggest buzzwords in tech today, neural networks and deep learning. You hear them thrown around all the time, often in the same sentence. But are they actually the same thing? And if they're not, why should you care? Well, let's crack this code together.
So, what is the real difference here? Is deep learning just a fancy marketing term for a neural network? It's a fair question. And the answer is actually, believe it or not, pretty simple. It all boils down to one single idea: depth. And by the end of this, you're going to know exactly what that means and why it is so powerful.
All right, here's the game plan. We're going to start with the absolute basics, the AI's fundamental building block. Then, we'll see how you arrange those blocks to build either a simple network or a deep one. After that, we'll get into the really cool part, how these things actually learn. We'll also look at some of the challenges they run into, and finally, we'll connect it all back to why this stuff matters in your everyday life.
Okay, first things first. Let's dig into the core component. Every single neural network, I don't care how big or complicated it is built from this one brain-inspired piece. And here it is, the artificial neuron. The easiest way to think about it is like a single brain cell, but for an AI. It's just a tiny little node that takes in signals from other neurons around it, does a quick, super simple calculation, and then decides if it should fire off a new signal of its own. That's it. This one little piece is the key to, well, everything.
So here's the process in 3 quick steps. First, the neuron gets a bunch of incoming signals. You can just think of them as data inputs. Now, not all signals are created equal. Each one has a weight that tells the neuron how important it is. Step 2, the neuron adds up all these weighted signals. And finally, step 3, if that total sum is strong enough, if it crosses a certain threshold, the neuron fires, sending its own signal down the line to the next set of neurons. Simple, right?
So we've got our basic building block. But, a single neuron on its own isn't going to change the world. The real magic, the intelligence, starts to happen when we connect them together into layers. And this right here is where we finally see the big difference between a neural network and deep learning. And boom, here it is, the big reveal. On the left, you've got your standard, simple neural network. It's got an input layer where the data comes in, an output layer where the answer comes out, and just one so-called hidden layer of neurons in the middle doing the work. And look at the right. A deep learning system has that same input and output layer, but it has multiple hidden layers stacked in between. That's the whole secret. The deep in deep learning literally just means the depth created by having more than one of these hidden layers.
And having this depth, this structure, lets us build all sorts of specialized tools. For example, convolutional neural networks, or CNNs, have layers that are specifically designed to find patterns like edges and textures, which makes them absolutely brilliant for understanding images and video. Then you've got recurrent neural networks, RNNs, which have these cool connections that loop back on themselves. This creates a kind of memory, making them perfect for handling things that come in a sequence, like human language.
And this all leads to a really important trade-off, right? The simple networks are way faster to train and don't need a ton of data. They're great for basic stuff. But deep learning systems, even though they're much slower and hungrier for data, can handle tasks that are just wildly more complex. See, each extra layer gives the network a chance to learn more and more abstract features. It might learn lines in the first layer, shapes in the next, and then full-blown objects by the end.
Okay, so having all these layers is one thing, but how does a network go from being a random collection of neurons to something that can actually learn? This process right here is the true aha moment of modern AI.
The magic behind it all is an algorithm called backpropagation. So imagine the network takes a guess. You show it a picture of a cat, and it says, that's a dog. Backpropagation is the process that looks at that wrong answer, measures how wrong it was, and then sends a feedback signal backwards through the entire network. It tells every single neuron, hey, you were part of this mistake, and here's how you need to adjust to get it right next time.
So this creates this awesome continuous learning loop. The network makes a prediction, it measures its own mistake, it sends that feedback backwards through backpropagation, and then it adjusts all its tiny internal connections, those weights we talked about. And it just does this over and over and over again, thousands, maybe millions of times, getting a tiny bit smarter, a tiny bit less wrong with every single pass, until it's making predictions with incredible accuracy.
But this learning process, it's not always a walk in the park. Just like for us, learning can be really hard for an AI, and it comes with its own unique set of problems.
So in these really deep networks, that feedback signal has a long way to travel. Sometimes, by the time it gets to the very first layers, it's faded to a tiny whisper. That's called a vanishing gradient, and those early layers basically stop learning. The opposite can happen too. the signal can get amplified as it goes back, becoming a deafening shout that just throws the whole system into chaos. That's an exploding gradient. And you can even have neurons that just get stuck and stop firing completely, like they're asleep on the job.
But of course, for every one of these problems, engineers have come up with some really clever solutions. One of my favorites is called dropout. Basically, while the network is training, you randomly turn off a bunch of neurons, just temporarily ignore them. I know, it sounds crazy, but what it does is it stops any single neuron from becoming too powerful or too specialized. It forces the whole team to work together and finding a much stronger, more flexible solution.
So we've gone all the way from a single artificial neuron to these massive, deep networks and the challenges of training them. But why does any of this nitty-gritty detail actually matter? Well, because this stuff isn't just in a lab anymore. It is completely woven into the fabric of our world.
Remember those deep CNNs we talked about? They are literally the eyes of a self-driving car. That deep, layered structure is perfect for sifting through all the visual data from cameras and sensors, spotting pedestrians, reading street signs, and tracking other cars all in real time.
And anytime you talk to your phone or your smart speaker? Yep, that's a deep, recurrent neural network listening. Its special memory-like structure is what lets it piece together the sequence of sounds in your voice and figure out what you're actually asking it to do.
And in medicine, wow, deep learning is an absolute game changer. These systems can analyze medical scans, like X-rays and MRIs, and spot incredibly subtle patterns that might be early signs of a disease like cancer, sometimes with an accuracy that can meet or even beat a human expert.
So when you really think about it, whether it's translating a language on the fly, spotting a fraudulent charge on your credit card, or even just recommending a new show for you to watch, the core principle is the same. It's the depth of these networks that gives them the power to make sense of huge amounts of data and perform these incredibly complex jobs that not long ago we thought only humans could do.
And this technology is moving at a breakneck speed. What we're seeing today is really just the beginning. It really makes you stop and wonder, right? If networks with a few hundred layers can do all of this, what happens when we build them with thousands of layers, or millions? What kind of problems will we be able to solve then?